welcome to another live stream on Sunday afternoon. Thank you so much for everybody who is joining me on YouTube. Please like, comment and subscribe if you haven't already. Also, if you look in the description, there should be a link to my Patreon. So welcome to all of my Patreon viewers as well. Thank you very much for your continued support. Over on Patreon, what we do is a full live lesson every week at this time. And the lesson is about double the amount of time on Patreon. So today what we're going to be doing for the YouTube crowd is we're going to be looking at rounding, estimating and bounds for GCSE maths. I'm going to be going over the theory for all three of those topics. We'll look at a couple of different questions and then the lesson will end for the YouTubers. But anyone watching on Patreon will then have an opportunity to work through a worksheet I've created. Not that one, we will look at that one as well, but we're going to be looking at the mystery of the missing jewels, which is just a fun way of putting all of that knowledge together. And then we will be running through some GCSE questions. Let me move my captions above there, but I don't want them to be that big. That's huge. Let me make those smaller. It's just the issue live streaming. All has to be done there and then. So these have got the same issue as well. Going to move those over. Everybody on YouTube won't have this, so apologies to anyone watching live. Okay, so once we've gone through the missing jewels worksheet, we'll also be looking at these GCSE style questions, primarily on the subject of bounds, as that's probably the hardest thing that we're going to go through today. Relatively speaking, estimating, rounding and estimating is a slightly easier concept, but we will be using that in the bounds questions, but bounds questions can be a little more involved and complex. So we'll go over some of those at the end for the Patreon crowd. Okay, so to get started then, what we're going to do is we are going to start with rounding. So I'm going to go over here and I'm just going to write down essentially the definition of rounding. And if you've got your notebooks handy, that's probably good moment to make some notes to begin with. So, okay, rounding. What is rounding? Rounding is essentially, well, it's either rounding a number up or down in order to get an estimated value of a number. So rounding and estimation are very similar. The reason we do round is that often we end up with decimalized numbers that have an infinite amount or a huge amount of decimal places. And it's actually quite difficult to calculate particular things with a number that large or with that many digits, particularly if you're not using a calculator. So rounding numbers can help us to find an estimation to a good degree of accuracy without having to deal with so many digits after the decimal place. Because after a point in decimalized numbers, those extra digits, they sort of become negligible and we only really need to worry about a few decimal places anyway. Of course, we can also round to place values of larger value than that, so it's not just about decimalized numbers. We might say, let's round that number to the nearest 10, so that it allows us to do simpler calculations when we estimate. So rounding and estimation are quite difficult to separate. They're kind of part and parcel of the same thing. We use rounding in order to estimate, and estimation requires rounding. So I'm just going to write down as a quick definition, finding an approximate value of a more exact value by rounding to one particular place value. So in order to understand this topic, you're going to have a relatively good understanding of place value, which I imagine most of you already do from primary school, etc. But I can just run through that now in a moment. So I'll just write a number down then, shall I? So let's do, in fact, I'm going to do this with my pen. Okay, so let's say I had the number 3,872.569. I'm just going to label my place values here. So because I have 3,000, this column here is the thousands column. Okay, then I have the hundreds because I've got 800. I have the tens. I have the ones. I then have the tenths. So the first place value after the decimal place is the tenths. Imagine it like a fraction. Then we have the hundredths. So it's kind of this in reverse. So that you guessed it, we then have the thousandths. Okay. Normally when we round with decimal places, though, the question won't necessarily say to the nearest tenth, although sometimes it does. It might say to one decimal place. And so one decimal place would mean the tenths, two decimal place would mean up to the hundredths, and three decimal places up to the thousands, etc., because obviously this goes on and on and on. Okay, so let's say, for example, leave that there for a moment. Let's say I want to round to the nearest, I'm going to write a few examples down, round to the nearest 100, and I have 5,781. Round to the nearest 10, I might have 876. Round to the nearest whole number, which means that you're always considering the ones column. 673.67. And then we'll just round to one decimal place. So we have 78.923. Now, of course, what I haven't written down is how we decide how to round. Okay, so finding an approximate value of a more accurate value by rounding to one particular place value. So if the question says round to the nearest 100, the place value we are concerned with is the hundreds column. That's the place value we want to look at. What we're also then concerned with is the place value directly to the right of that number. So the number to the right of our place value is going to decide whether our number rounds up or stays the same. Now, I'm going to write that down and then I'll show you and explain it. So it's a good note to get this written down as we go. So when considering whether the digit in your place value either stays the same or rounds up to the next digit, you must look to the digit directly to its right. So if that number is between 0 and 4, our digit stays the same. If that number is between 5 and 9, our digit goes up. So if we look at that in practice, what that means is, let's say we had 765 and I wanted to round to the nearest 10. So from rounding to the nearest 10, I'm focused on my tens column, okay, the place value in the tens. So this is the number that I'm deciding is either going to stay the same or go up. So 6 is either going to remain 6 or it's going to go up to 7. Those are the only options. It doesn't go down, it just stays the same. So in order to decide that, I need to look to the number directly to its right, which in this case, that might have not looked like right on my, because the camera's doing it all back to front, so that will look like left. But I am actually pointing to my right. Because it's a 5, that means that it's in the group. That means our 6 goes up. So rounded to the nearest 10, this becomes 770. Okay. Let's look at this one. Round to the nearest 100. So I'm concerned with the hundreds column. That's the place value I'm looking at. Now 7 happens to be my digit in the hundreds column. So I'm deciding whether 7 goes up or stays the same. So in order to decide that, I have to look to the number to its right. The number happens to be 8. Now 8 is between 5 and 9, which means the number goes up. 7 goes up. So to the nearest 100 is 5,800. This to the nearest 10. So the tens column is my 7. And so I look to the number directly to its right to decide if it goes up or stays the same. This is a 6, which is between 5 and 9, which means it goes up. So it's going up to 8. So it's 880. This to the nearest whole number. We're thinking about whole number, we're concerned with the ones column as the place value, so we look at the number directly to its right, which happens to be 6. So because 6 is between 5 and 9, the 3 rounds up. So to the nearest whole number, this would be 674. Rounding this to one decimal place. If I'm doing one decimal place, the place value I'm concerned with is the first decimal digit, which is 9. I then look the digit directly to its right to decide if it stays the same or rounds up. Now this time it's a 2, which means it's between 0 and 4, which means the 9 stays the same. So to one decimal place, this is 78.9. Okay. So what I'm going to do is I'm just going to give you a few other examples of those, and I'm going to see if you can round them yourself, and then I will quickly go through them afterwards. So I want that to the nearest 100, that to the nearest 10, that to the nearest whole number, and that to one decimal place. Okay, so I'm just going to give you a minute now. Once I stop speaking, you will be able to see the oh no, you can see all of them. That's good. My captions haven't gone over that. So I will give you a couple of minutes and then I will go over them myself. Okay, right, let's have a quick look at those then. So we have this rounded to the nearest 100, so I'm looking at the hundreds column. I look at the 3 next to it, that's between 0 and 4, so therefore it rounds down, so it's 9,800. Round to the nearest 10, so my tens column is 5. I look to the number next to it, that's between 0 and 4, so it rounds down, or stays the same rather, so it's 750. Round to the nearest whole number, so I'm looking at the ones column to consider the whole number. I look to the number next to it on the right, that's an 8, so that's above 5. It's between 5 and 9, which means the number will round up, so it'll be 655. Round to one decimal place. One decimal place, I'm looking at that place value there. I'm then looking at the number next to it. That's between 5 and 9, so that means it goes up. So to one decimal place, this number is 789.5. Okay, cool. So that's rounding. So why that's useful is because of estimating. So we'll just write a little note about estimating. So estimating is a method of calculating an approximate answer to a more complex calculation. So it involves rounding the numbers within the calculation or doing any operations to make those calculations easier. Okay, so the whole point of estimating is to make it easier and to give us an approximate answer if we don't need it to be exact. Okay, so let's say, for example, I wanted to work out 789 multiplied by 592. Okay, now a question might say, using, this is how they might word it, using estimation, work out the following. So they put it underneath, to a reasonable degree of accuracy. So reasonable degree isn't necessarily pushing you towards exactly how they want you to round it. So different people might round these differently. For me, looking at these, because the digits are so large in the tens column, it makes sense to round them both up to the nearest 100, but you might decide to round them to the nearest 10. What you can't do is keep those numbers the same and just do the calculation. You could do that, of course, but you won't get the marks for that because the question is specifically asking you to use estimation. So therefore, we have to round those numbers first. So what I'm going to do, what I consider a reasonable degree of accuracy, is to round them both to the nearest 100. So if I'm rounding to the nearest 100, I look at the hundreds column. I look at the number next to it. That 8 is between 5 and 9. So the 7 rounds up. So what I actually have is 800 multiplied by 600. Because that 592 is going to round up to 600 because of this 9 in the tens column. So 800 times 600 is much easier to calculate. I can just do 8 times 6, add 4 zeros on the end. So 8 times 6 is 48. With 4 zeros, that's 480,000. Okay, which isn't obviously the answer for this question, but is an approximation to a reasonable degree of accuracy. Okay, so there is some leeway here in terms of how you want to round it. You could have made a decision to round this to the nearest 10, but actually that wouldn't have helped us much because 790 times 590 isn't an easy question still. It's not something you can do quickly. The whole point of estimation as well is about being able to do the question quickly if you need to. Okay, right. So let me give you some examples or some questions to do. So 48 minus 36. Obviously you could do that quite easily, but do it with estimation. That's the challenge. 5,782 multiplied by 9,428. I'll do one more. So we'll do 24,962 divided by, let me get my division symbol out, divided by 8,231. Okay. Right, so I'm going to give you a few minutes to do those, and then I'll show you what I would do, and then we'll have a look at bounds, which brings in the rounding, but it's how we show the upper and lower bound for particular measurements, etc. So we'll get into that in a minute. So just have a go at doing those estimating for me, and then we'll move on. Okay, right, let's have a look. So, right, so 48 minus 36, I'm going to decide to round that to the nearest 10. So that ends up being 50 minus 40, which is 10. We actually compare that to the real answer is 12, so that's not too far off. Okay, so 10 is an approximation. Shouldn't really be putting equals there, although that does equal that, doesn't it? But normally with an approximation we do squiggly equal sign, which is what we would have here if we said that equaled 10. I don't know if I've got that to hand right now. Doesn't look like it. That's fine. I can find that later. Okay, so this one I would probably round to the nearest 1,000. Ideally, you want to be dealing with one digit, right? Because we all know our times tables really quickly. You're still going to spend time working something out if it's 2 digits at least. So I think rounding things to one significant figure, which is not something I've gone over actually, but that just means that there's one digit that isn't a 0. So all the rest are zeros. The first digit is a significant figure that's not 0. That can help you because you can just simply do, as we did there, 5 times 4. 5 minus 4 is 1 and it's 10. But with multiplication, this makes more sense. So if I rounded this to the nearest 1,000, that's one significant figure because it's just 6. And then this would be 9,000. So I'm actually just doing 6 times 9, and then I can put my zeros on the end. So 6 times 9 is 54. I've got 6 zeros, so that's 54 million. Okay. A little note to bear in mind when we're talking about significant figures, zeros aren't significant unless they're in the middle of a set of numbers. So if I'll just go down here a minute. If I had 0.00708, all of these are insignificant, the first 4, because they are before any other digits. As soon as the digits begin, if you have zeros after that and between other zeros, that 0 is now significant because it's holding a place value. If I had a 0 afterwards, that's not significant. So zeros either side of digits are insignificant. Zeros in the middle of a sequence of digits are always significant. Okay, that's just a little note there. Okay, this one I'm actually going to do to the nearest 1,000 on both of them, which is a slightly different thing to do. Simply because one of them has a 10,000s column, the other one only has a 1,000s column. I think my aim when I wrote this question was to have 24,000 divided by 8,000, which would have been nice because 24 divided by 8 is 3. But I haven't done that because I put 9 in the hundreds column, so that's fine. So I'm actually going to round that to 25,000. And then that's going to get divided by 8,000 because that 8,000 is going to round down. So I've got 25,000 divided by 8,000, which is essentially 8 divided by 25. So that will actually give you the same answer. So if I just wrote down 25 divided by 8, whatever I get there will be the same as 25,000 divided by 8,000, because there'll be the same number of 8,000s and 25,000s as there are 8 in 25. So let's just do a quick bus stop, see if we can get a nice number here. I don't think we will. So there's 3 with a remainder of 1, 1 in 10, remainder of 2, 2 with a remainder of 4, 5. So the answer would be 3.125-ish. Okay, so the decimal number that you'd get for the actual answer would be similar, but it would be a little bit different to that. Okay, let's hope it'll at least be 3.1. So that's estimating. Right, we're going to move on to bounds now. So I'm going to make a new note in your notebooks. Just move that around, I suppose. Okay, so bounds. So bounds are sometimes also called limits. They are the limits at which, if a number has been rounded, what are the limits of what the original number could have been? So these present the possible values of a number before it has been rounded. And what we do is we think about the biggest number it could be and the smallest number it could be. So, for example, if I said my number is 770 rounded to the nearest 10, that means that the original number would have not been 770. It would have been something that rounds to that. So when we're thinking about the digit next to it, the biggest number that could have been is 774, right? And so this is a mistake some people make. First of all, the lower bound, the smallest number it could have been, would be 765, because that 5 would have rounded the 6 up to become 770. So that's the smallest number it could have been, because had it been 764, it would have rounded down and the 6 would have stayed the same. The upper bound, however, this is where people get confused, is actually 775, not 774. Now, the reason for that is that because, let's say we had 774.999999999999999, and it just went on and on and on forever, that would still round down to 770. So actually 774 is not the biggest number. This is the biggest number, that infinite number of nines. So what we like to call the upper bound is 775. Anything below that can round down to 770. It can't be that. It can't be 775. But we use it as a place, also almost estimation, I suppose. We use it as the upper bound because the biggest number it could be is just impossible to write down. Okay. Now, when we write this algebraically, what we would say is we'd go 765, and we're going to call x the original number. Now, what I need to find is some inequality symbols here that help me to illustrate my point. So I want something like that, but not quite like that. So, am I going to find my inequality symbol? If I don't, I'll just write it. I need to find my maths ones. Okay. Something like that. Oh, these are squiggly equals. That's what I was looking for earlier. There you go. But that's fine. We don't need that now. Yeah, no, it's not there. That's fine. I'm going to do it with my pen. So, our value of x, our original number, is bigger than 765. Okay. So it's anything that's bigger than that, but it could also include 765. So we put a line underneath it to say it could also be equal to. So x is either equal to or bigger than 765. But over here, when we do the upper bound, we just say it's smaller than, that was rubbish. We just say it's smaller than 775. So we don't say that it's equal to in the same way we do with the lower bound, because it isn't equal to, because if it were 775, it would then round up to 780. Okay, I hope that's making sense. So what I'm going to do now is I'm going to write a few rounding examples. I just want you to write down for me the lower bound and the upper bound for both of these. So the lower bound and the upper bound for 543.2 to one decimal place. And I want the lower bound and upper bound. I'll write it like this so you can kind of lay it out like that. And then I want 6,249 to the nearest 100. That's not what I want us to do, is it? That would be rounding it. 6,200 to the nearest 100. I want the lower bound of that. And then I want the upper bound of that. Okay. I'm just going to give you a couple of minutes now. And then that will be nearly the end of this YouTube video. I'll just show you how you might use that in a question before we just switch to the Patreon crowd. Okay, right, so let's have a little look at these. So 543.2 to one decimal place. The lower bound of that, the smallest number it could be, would be 543.15, and that would be the smallest number that would round up to 0.2. The upper bound then is 543.25. So again, that wouldn't round down to 0.2, but anything below that, even fractionally below that, would. So that's what we call the upper bound. To the nearest 100, the smallest number it could be would be 6,150, and the upper bound is 6,250. Okay, so it's always like 5. 5 is always your crucial digit to use when looking at these upper and lower bounds. So let's put this into one example before we finish the YouTube video. So let's say that this is the width. Oh, sorry, spell width of a garden. And this is the length of a garden. Now, a question might say, calculate the maximum area. Or it might say, calculate the minimum area. Okay, so in order to calculate the maximum and minimum of an answer, what you have to do is find the two values that are going to give you the biggest answer or the smallest, depending on what the question is asking. So the maximum area here is going to be the two upper bounds multiplied together, which would be 543.25 multiplied by 6250. I'm not going to work that out just in the interest of time, but that would give you your maximum. Similarly, the minimum would be 543.15 multiplied by the other minimum, which is 6150. Okay, so that would be how you'd find the maximum and minimum. One other thing to note is that depending on the scenario in the question, if a division is involved, you need to be careful about which bound you're using to get the maximum and minimum. So let's say, for example, that instead of the width of a garden, this was the distance ran by someone, and then this was this might not be realistic, I'm not a runner, the number of seconds it took. Okay, so if it said calculate the maximum speed or the minimum speed, we'd need to think about which bounds would give us the biggest number. So remember the distance speed time triangle. We have distance over speed times time. So to find the speed, we'd need to do distance divided by time, right? So in order to get the maximum speed, we need the upper bound divided by the lower bound, because a bigger number divided by a littler number is going to give you a bigger answer than not dividing it by a bigger number. So, and logically that makes sense. If someone's gone a really far distance in less time, that means they've run faster, so the speed is going to be higher. So the maximum speed here would be 543.25 divided by the lower bound for the seconds, which would be 6,150. And similarly, to get the minimum time, it would be the least amount of distance run, so 543.15 divided by the most amount of time, 6,250. So it really does depend on the scenario in the question as to which of the bounds you choose from each value in order to get your maximum and minimum. Okay, so thank you very much, everybody on YouTube. Please like, comment, and subscribe if you haven't already, and come and join us on Patreon. The link is in the description below. We'd really love to see you there. It's just £7 a month to get the full video of what we're doing here. So I'm about to embark on some worksheets and some GCSE style questions just to put some of this theory that we've been going over into practice, which of course is what maths is all about. So making sure that we can actually do the work rather than just understand it up here. Okay, so thank you very much. Hope you have a lovely week. I'll see you next week for another English lesson.